Hello boys and girls. In this video we're going to talk about private key, public key cryptography, and in particular we're going to sign a message. That's what you can do with this scheme. Of course it relates also to blockchain technology in that such schemes are used to have users for their account sign transactions cryptographically and thus allow a change of the global blockchain state. So, you know, you own stuff on an account by virtue of having a private key. You sign the wish that you want to move some funds around out of your account, broadcast it to the network. They receive it, check if the signature is all valid, and then actually locally change their state after a consensus process. But an important point is that the whole spiel is really independent of blockchain, in that it's just a scheme to sign messages and have them verified on the other end in a way that it is certain that only the people who own the private keys, to the extent that the private keys is safe, can actually have signed the message. And it's also older than all these distributed ledger games. And also this does not only work with elliptic curve cryptography, but there are also other schemes which are quite close most of the time to elliptic curve cryptography, as it was first used on the Bitcoin blockchain, and Ethereum uses the same curve. And so I think there's a lot of uncertainty around it, because the users, maybe they're on a web wallet or some wallet app. You just press buttons, then they get this strange looking string of random looking characters, and it's used like a password in a way that it is what it is. And today I will want to show you what it means to sign something with that and how that works. I mean, I have made a video about the algorithm behind signing on the elliptic curve in the past, like a math video. I will not do any math really in this video. But want to make the video to have people get a little bit more certain about what they are dealing with here, and what is important, what is not important, and what is the underlying concepts. And also, since likely in the future, if people can generate private keys easily on Calibra, if they have a Facebook account, even if they have nothing to do with crypto, then they will have the tools in hand to sign not just transactions on this ledger, but to sign anything, like any document, right? As soon as there's an association between, I know your customer, identified real person, and the private key that they're said to own, then they can use the private key to sign any message, from a crypto transaction to statements like, I really hate cake, or whatever it is. And so this is going to be relevant, and I want also to emphasize, I had some discussions with that in the last weeks, that having people being integrated in a network and the technology that is blockchain space, then suddenly a lot of people have a lot of more tools, and this will also affect what other tools are not technically possible, because they're already possible, but practically to be translated to different models. Okay, so I guess having all that said, let's get into it. Want to point out that I have here this video on the algorithm, the math video. I have also did a live coding of SHA-2, like on the bit level, exactly how it works. In the past, I've also made more videos about hashing. So there's videos that are not necessary but helpful to get technical details on this video. And otherwise, subscribe to my channel and like the video and so on and so forth. So I want to start with this web page. Let me just go on the start side here. So there is this page. A bunch of people in the crypto space know this. It's called keys.lol, where they say, you know, all private keys are on this website, and you know there are too many private keys. If they all use up a few bytes, then there's just too many private keys to store. So it's not the case that this guy has a server where they're all private keys. But what this web page does is, given any private key, he computes the corresponding public key, and this is just the relation that comes with the public key, private key cryptography. And then if you're in crypto, then this public key is also again hashed, and this is turned into the address that can hold funds on the blockchain. And what this guy does is takes any private key, turns it into a public key, turns it into an address, and then you can on this page then look up how much funds are on the respective blockchain. So if you go on a random page here, then he generates a random private key. So this is a private key. There's an underlying corresponding public key, and then there's this address. We can on this side even go on the Ethereum blockchain corresponding to that address, and we see, well, since this is a randomly generated private key and there are like so many private keys, this is it would be magical if that has been used in the past by someone. So what you see here is an Ethereum account that has no funds whatsoever, and nothing ever happened here. And so we're going to deal with this format here. This is a Ethereum format private key, and that has certain conditions on how long it has to be. So I'm quickly going to go over to Python. So this is my editor. Here I can run the script as I code it. So for example, I can print out this private key that I just copied from the website. If I do that, well, we'll just print it here, and I might take this on or print the length of it. So, and here we see the Ethereum private key has 64 characters. And so before we get more into the Ethereum private key, and it's the same on all kind of platforms, there's one semi-mathy things that you have to understand, and I talked about this in other videos, and it might be obvious to some and not to others, so I will give a short rant on that. That you can take any number, like let's say 77 objects, 77 books, and in decimal representations, you know, 10 digits, that is represented as a 7 followed by a 7, 77, right? This is 7. That's what we mean by 77 decimal number of objects. But you might also translate it to some other base. So for example, if you don't use 10 digits, not 0 to 9, but only 2, right? 0 and 1, then you can use the same scheme of longer and longer sequences of digits to represent the same number. So for example, what I can do here in Python is I print, I can print 77 and it will give me 77, okay. But I can also convert this to binary. And then it says 0b, this is just a prefix to tell me this, whatever follows is in binary. And then the sequence 0, 1, 0, 0, 1, 1, 0, 1, this is just the number 77, but expressed in another base. Since there are fewer characters, only 2, 0s and 1s, this will get longer. And if you use more than 10 characters, like will be the case with hexadecimal, like where we use 16 characters to express numbers, then this means these numbers can be represented in a shorter way. So for example, we can convert this to hex, and then the same number 77 is expressed as 4D. So I just want to emphasize that in all these cases we might use this representation to speak of 77 objects, 77 books. So the same amount, quantity, but how we represent it, like what 77 means, is like the amount is fixed, but the representation is different. So 4D in hex is also 77 books, but our convention is just to use the decimal system. Our convention is just to use the 10 digits. So 77 number of things, but the representation might look different in different bases. Okay, so that said, I mean, I can show you more numbers in the representation. So I will go through 20 numbers. So for the number n in this range from 0 to 19, print the number n, print it also in binary, and print it also in hex. So if I do that, then I see the number 1 in binary is the number 0 in binary is 0, and in hexadecimal as well. The number 1 in binary is 1 in hexadecimal as well. The number 2 in binary, there is no character 2 to represent 2. So this is actually 1 0, or quotes and quotes 10, 1 0. The number that comes after all the characters is used must add more digits. But in hexadecimal, since hexadecimal has actually 16 different characters, it's still just represented as a 2. And if you go on and then to the number 11, for example, the number 11 in binary already has 4 characters. It's like 1 0 1 1. But in hexadecimal, it still only has 1 character because there are more characters to choose from. So after 9 comes 10, which is an A, and then after 10 comes 11, which is a B, and so on and so forth. And if I go up to, let's say 100 here, let's look at the first 100 integers. Then, for example, the 77th decimal is represented as this sequence of zeros and ones in binary, and in hexadecimal it's 4D. It's also 2 characters. And if we then go up to 1000, let's look at the first 1000. The number 969 in binary is already a pretty long string, and in bad example because in hexadecimal it's also still just 3. So let's go up to 1 million or what. Okay, so here the number 999,999 has obviously 6 characters in decimal. It has, I don't know what, 20 or so characters in binary, and just 5 in hexadecimal. So you see, with the more characters you have, the bigger your alphabet is, the less you need. And so this is a way of compressing information. And so, for example, as we have in Ethereum, private keys that look like this, with just characters from 0 to F, so these 16 characters, they have a certain length. And if I were to convert this private key to base 57, then I would have to add more characters, but I could also make it smaller. And this is actually what happens, for example, on the Bitcoin blockchain. In Ethereum, I think they had that on the to-do list, but they never did it. They just deal with hexadecimal numbers everywhere. And then on Bitcoin, they have more translations, and they also have different format for addresses. And so this is more concise. But the main takeaway is that if you look at a private key like that, then this is really just another number, right? This is just a number expressed as a hexadecimal string, is also say, you know, hex string. And similarly, the private key is turned to a public key. That's also just a number, and this is then hashed to an address, and this is naturally hexadecimal expression, but it can also be interpreted just as a number. We are only dealing with numbers here. This is my main point that I wanted to make in the last 5 minutes here. Okay, so that said, I would say let's get into it. We are going to come up with some message that we are sign with a private key. Okay, before that, okay, let's say our message is some random message. So I will define a value here, a constant. And this is going to be, you know, some message or information that I will sign. This can be anything. Can be any sequence of bits, really, or sequence of bytes on the normal architectures. So this the input for signing doesn't have to be a text in that sense, but just some byte array, and that's why this also takes a byte array as input. So I have to do a Python conversion to byte array. This is what this B is here, but it should not concern you very much. And also, by the way, sorry for the unprofessional showing of my recording tool here, but since I have two tools here, this will sometimes stick around. Okay, this is the message that we're going to sign, but before we can sign, we are going to have to get a private key, right? We need something like we saw, this string of 64 characters in hexadecimal. And you know what this page does is it just generates a random private key, like, and if like from 1 to any particular size. This is something under expressed in binary. It would be 2 to the power of 256. It's a huge number. Something between 1 and 256 is a valid private key. And what it does here on this web page is it just generates a random private key. And then, since this is just a number and it goes on like this, you know, you can enumerate them and go through them. He just generates all this private keys and then enables you to right click and go on the corresponding Etherscan, which will be generally 0 if the private key is a random one, because it's not really possible that accidentally you get to one that has some funds. And if you go then to the first site, then we see the first private key. So since these hexadecimal expressions, the private keys are just numbers expressed in some format, they start somewhere, and the legal private keys on Ethereum and also Bitcoin start at 1. So this is already a legal private key, and since it has such a simple simple structure, because it's just like literally just a number 1, it has a public key associated with it, and then this is hashed to some ugly address, and because it's known, this has actually already been used. So there on this I see there are actually some token there, probably worth nothing, but there have been 700 transactions on the address with private key number 1, because it's like it's natural maybe to use this as a testing tool for stuff. And similarly, like all the earlier keys, like if you go at private key number 10, then these just have been like used for testing and moving funds around and invoking stuff. But of course, if you then go to some random private key where all these are not zeros but much more randomly chosen characters, then you will have a generic address, and nobody has ever looked at that because that would be a strange accident. Okay, so if you are on some web browser or some website, then you you might have done that before. You make an account and it gives you some random private key. It looks random because that is what makes it safe. And we are also now just going to create actually a private key that's a valid one, and maybe one that looks prettier than a generic one, so less safe. But just so you see like how that what happens on this wallet might be web wallet or some app. It's just they have some random number generator. Maybe it's more clever than the Python one that we're going to use, but the idea is just to generate a random number, right? So before we can do that, I will code up a utility function for me, for us here, to print out some information about the objects that we're going to work with. So I define a function called show that you pass a value, and it will print out the value of this variable. Then it will print out the type, because we convert so much between formats, and then it will also try to print out, since this is a characteristic of private keys and public keys and whatnot, the length. But since not all objects that we are going to look at will have a length natively, I have to do the following. I make a try statement. It should try to print the length of the variable, but if that doesn't work, then I'll do the following. Try to first convert the variable to a string, and if that also does not work, then just do nothing, pass. So this is just this helper function, this show function. For example, I can do show me the message that I have written down there, and if I do that, then Jesus, I have to delete this because otherwise he will compute this every time. So after he, I can do this again. I let him show me this message. The message was exactly this byte array, and it tells me about the type of this, or the class, which is the same in Python, is bytes, and this has 50 characters, or length 50. Okay. So now that we have that, we are going to, I'll show you how it looks like if you generate a random private key, right? So we are going to import the random module from Python. And what is our approach? Well, what I'm going to do is I will generate a random number, right? I use the random number generator from Python. Generate a huge random number, because we have to eventually convert it back to hexadecimal. So what I do is I generate a longer number, I will convert it to hex, and then just cut off some of the characters to get a valid private key, which means it has to have 64 characters. So I say random int, and he already knows the names that I want to use, because I have already dumped them in this file. So I have an easier time coding things up. Just if you're wondering, I'm going to use the random module, and there's a function called randint, and so we'll generate a random number between 1 and then some huge number, 2 to the power of 300. That will give me a random number that is actually longer than what I want, because the private keys with 64 characters in hexadecimal translates to, in binary, to a private key of 256 zeros or ones. So there are 2 to the power, like a little bit more, less than 2 to the power of 256 private keys. Like this is this huge number, and that's where the safety comes in, because it's impossible to guess from this huge amount of keys. So if I generate a random number between this, then I have certainly the range is already bigger than there are private keys. And if I do this, and one note, whenever I will run this script, he will generate a new private key for now. Just if you be aware of that. So I generate this huge number. This is an integer. It has 90 characters in decimal. If I convert that now to hex, then do the same thing, right? I run this, it generates a decimal random number, convert this to hex, so these two numbers are the same but just expressed in different formats. And here it only has 77 characters anymore, because it's a more concise format. And now I will generate a valid Ethereum private key by just dropping off numbers. And for the lulz, I will what I will do is I will generate a valid private key which actually starts with the word coffee and ends with the word coffee, because the letters in coffee are all in the alphabet from 0 to 9, and then A, B, C, D, E, F, right? Coffee only needs cafe, so I will use cafe. So C-A-F-E, and in this way I get a private key which is a little bit more special. It's not super random and does actually loses strength, but nevertheless will be impossible to guess because everything between cafe and cafe will be random letters. So this is not a recommendation, and also regarding this, it is not a recommendation to generate a private key like that, but for explanation's sake. And also here, if there is a possibility of an option to enter your private key, don't do it, obviously. Don't enter your private key on any random website. Okay, so let's say random private key hex. So this is already now a proper private key. I abbreviated with PRV because I would say P, but public key is also starting with P, so this is a little bit annoying. And I said, I write cafe. Then comes whatever hex is generated here. So as you can see here, they actually append this 0x representing hex. So actually we have to start at the third character here. So we start with index 2 and go to, well, we are interested in 64 characters, and then we have to subtract 4 from this cafe, and then another 4 from cafe at the end. And we will show this then. Right, and so here we have a nice private key for the Ethereum blockchain, right? Cafe, blah, blah, blah. And this is just what we have here, starting with 6.3 da 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 to here, I think. No, yeah, here. So this is the bulk of the key. Then I have appended these 8 characters, cafe and cafe at all ends, just for that we can recognize this is somewhat special. And so this is just another private key, and you might append, if you like, 0x if you want, right? So this is the generated one with 77 characters, and here 0x cafe, and then whatever b1 da, 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 and so on and so forth. So there you go. This way you can generate a private key. And I mean, again, I don't want to speak about the safety properties of some Python script, but not too much different is happening if you're using Ethereum, my Ether wallet, and they have some Java application where on the client side, hopefully they generate a random number and give you a corresponding private key like that. But you can also use just the word cafe with a bunch of zeros in front or whatnot. So since this is always generating a new random number, I will actually not use this for the rest of the video. So this was just the explanation for how to generate a private key. What we're actually going to do is we are going to use one of these earlier ones. So I think we have used the number, I talked about 77 before, so let's just show 77 again. No, 77. Come on. So 77 integer, 2 characters here. If I convert it to a hex, getting tired. Then in hexadecimal, 77 is 4D. I think we had that already. So if you look at these private keys here, the first private keys. By the way, the zeroth is invalid actually on the Ethereum and Bitcoin blockchain, and you cannot. You can actually not use the private key 0, and sadly it still has a valid address. And so, while this is an earlier but already emptied out address, this is another earlier and emptied out, this is some random address. Nothing ever happened here, nothing ever happened here. Since this is such an easy to generate private key, and since it corresponds to a valid address, but not any valid transactions can be made, this is hard coded into the blockchain protocols, that you cannot use the public key 0, which stems from the private key 0. You can actually never move funds out of these addresses, but people send some funds to it. So you can see here 10 Ether have been sent to this address, which corresponds to the 0 private key, and this is $3,000 that will never be removed unless the whole all nodes decide we do a software update and suddenly allow for the 0 address to be used, 0 public key to be used. To tell a similar story, there is actually 65 Bitcoin, I think roughly, on the Bitcoin address corresponding to the public key empty string. So empty string is not actually even a number, but in some old address like wallets, they are allowed to send funds, probably still do, to the address corresponding to the empty string. You have a private key, you go to a public key, the public key is some number, you hash the number, you get to the address, and the hash can also take the empty string, even if there is no number, and so you get an address which corresponds to no number. So there's no way, unless they actively decide to allow that, to move funds out of the empty string address, public key address. And so this is a lot of money that cannot be retrieved from the Ethereum block, from the Bitcoin blockchain. So this is just a story on the side. But yeah, so we are going to use the 77's public key, which in hexadecimals is 4D here, this one. So remember the address corresponding to this private key is 0xC2A something something. Because it's such an early address, people have used this to testing. So 400 days ago, people moved some tokens back and forth. But at the moment, all these have been retrieved, I guess. So this is probably just some random contract where somebody dumped some coins that you would not be able to sell anywhere. So this is just useless. Okay, so we're going to deal with this here. So let's do that. 77 private key, 4D is what we're going for. You know, 0x4D, of course, is not a valid private key. We have to append a bunch of zeros before that. And so, I'm going to define the private key which starts with 62 zeros, and then we have 4D, right? So this is a valid Ethereum private key. And what we're going to need is a library for, because I'm dealing with Ethereum, called ETH keys. So this is the library that holds the elliptic curve routines that we're going to use to transform from private key to public key and then also to address. And for your information, this is available. I mean, you can, if you know your way around Python, you can just pip install it, but you can also inspect the code at GitHub on the Ethereum org and then ETH keys. So this is a website where you can go. And also for your information, this is the name of the like the elliptic curve used for Ethereum. This is the same that it's used for Bitcoin. But again, everything that we do afterwards, we're not going to look at the elliptic curve math. We're just going to use it as a black box. More explanations are on this previous video that I did. And so there are infinitely many curves that you could use. And you don't even have to use elliptic curve cryptography. There are other private key, public key, like public key cryptography algorithms that don't even use elliptic curves, but other schemes. But not more on this in this video. So we have this keys library, and what they happen to want is the private key first translated as a byte array. So I will do them this favor and call this private key bin, or sequence of binary values or bytes, and inbuilt Python function is byte array and then from hex, and we're going to convert this hex private key that we just coded up. So I mean, in case you're interested in that, we can look at this binary, like byte array version of this, and this is going to be this key. So this is a byte array. This \x denotes the byte encoding in Python, and a bunch of zeros, and eventually something else, which is an M. So let's first look at, show this one. So, right, this is the private key that we're going to use in this format. As a byte array, it looks like that, but that doesn't really have to concern us much. But I'm now going to use this together with this Ethereum library to create, and here it gets a little bit into programming lingua, but this library has an object which has a bunch of member functions which do all the work of converting to public key and so on. So we're going to convert this into a private key from this ETH library. That's what this ETH ought to denote. So I use this library ETH keys, and from there I use the keys module, and then there's this member function private key, and where I pass this byte array private key. So here, all of what happens here is just conversion, right? Nothing happened here. It's still the same information as we have here. But if you look down here, it's format. That's the wrong one. If you print out this ETH representation, so there is this ETH keys data type private. This is not a private key, but as they want to use it in this library, right? In this class. But nevertheless, if you print it out, then it still tells you this is actually this private key here. Okay. And finally, with our private key in hand, converted to the format they want in the library, we can make a signature for the message. So what we're going to do now is here, we take the message. Here, this is the message we want to sign. We will put our stamp to it. We want to, maybe you correspond over the internet with somebody and they know you have this public key. Maybe you have it from some blockchain, or maybe you just did the communication or give it to you in real life in private. You said to him, hey, this is my public key, and I have the corresponding private key that I own, and the whole math allows you to take any byte array, in this case this message, the message that said some message or information that I will sign, bro, and you can generate then the signature which contains this message as well as a signature like a signature like your thumb that could have only come from this private key. And since it's practically impossible to find out the private key from the public key, then if somebody sees the signature and uses the algorithm to verify, oh, that has been signed with the private key, then it can be confirmed that the only people who own this private key have actually agreed to sign whatever message this is. Right? Makes sense? And in the case of a blockchain, same thing happens. Like by generating a private key, you generate a public key, you get an address. It's just some number representing an account, and then if people send funds to the blockchain entry with this address, then you are the only one, you that generated the private key are the only one who can sign information tied to the public key underlying the address. And the way this works then in the blockchain space is that only these people who own the private keys to the address, only their signed calls for transaction out of the address will be in the consensus even considered to be added to the shared state of the chain. Okay, I hope that makes sense. So in this library, it's very convenient to generate the signature. So we say my signature is we need the private key, of course, to sign it, and then sign message, and then we enter our message, and this could be any byte array. Show me the signature. Yeah, and so this is what comes out. This is the signed version of the message. Here in this thing, both the public key that corresponds to the private key is woven into it, as well as information about the message. You see this thing is actually longer because there's more information packaged into that thing in this signature. And if you know that I have the public, I should probably generate the public key first so that you can actually see have some more association with that. But basically the math is such that if I give you this signature and the message, then you can actually verify that only somebody who has the private key to the public key and address could have signed this, and thereby put validity to this message. Okay, so let me use this tool as well to just get the public key out of this. Maybe I should have done this first. So how do I want to? Yeah, it says public key, and this is also from this an ETH data type here, the private key, and then it's just public key. So very simple. Okay, so this thing is the public key corresponding to the private key, to this private key, right? We have coded up this private key, wrapped it into this Ethereum elliptic curve library, and this lets us compute the public key corresponding to the private key, and if this thing is hashed, then only then we get to the address, and we will also do this in a moment. So here the library obviously also has then this verification tool. So we can say we create a boolean, a yes no, as follows: verify sig, that's just my name for yes or no, and we take the signature, and the function is verify message, and we have the signature. We want to verify that this message was in the signature signed with the private key corresponding to this public key. And again, the public key can only be computed if you have the private key, and the other direction is practically infeasible. So if we now print out this, then we see this is actually correct. So you know, if we would change the message, if we'd say the message is, I don't know, good day, and run this, so then he doesn't even want, because this is not a byte array anymore. Byte array. So then it says, no, hey, this signature is not a signature of that message with this public key, right? So you see now you have the tools to, for every person where you know this person has a so and so public key, which he or she derives from the private key, then you can play this game that you can have them sign statements and say, you know, this actually came from me, and you can sign. You can add signatures in emails at the end, and this whenever you sign, the signature also looks a little bit different, because there comes also random number into play and so on and so forth. I talked a little bit about this in the other video, not going in detail about this, but so the whole scheme of as I just explained, is used on a blockchain to sign transactions, but you can sign anything with that. That is more general than that. And that's what I meant earlier. If everybody like has some account and some distributed ledger with this technology, then suddenly you can expect more people to be able to actually digitally sign stuff, to the extent that they are know your customer, if that's relevant to you anyway. Like on Bitcoin blockchain, that nobody even cares who's the person behind that. Okay. So lastly, from the signature and the message, you can actually also recover the public key. So I will also do that. So I say cover public key, and that's, we need again the signature and another function here that's called recover public key from message. And if you pass here the message, then this, if this is a valid signature and this is a message, then the public key is baked into the signature. So this thing will actually return some public key. And so if I say this should be equal to the public key, the if public key, then if this is proper, as it is in this case, then this will return true, right? So if I go show me this value, then it will tell me that works out. This is both true. Okay, and finally, we can get the address from this as well. So we say public key if, and then that's the wrong one, this public key, to check some address. Okay, this is just a simple method with no arguments, and then show me the address. Well, this returns this address. So the private key, the private key came down to, I print this again here. Sorry, show Chuck. So into many row. The private key 77, the 77's private key came down to this public key, and this gets then hashed to this address. And indeed, this is also what this website here computed. So they use probably JavaScript or something and do the same sort of computation. They use some library, and here I've just did the same thing with Python. And so finally, at the end of this video, I also want to show you a quick hack to actually check if this address already has been used in the past. So because it's so easy, I will just add this here at the end of the library, at the end of the video. What we're going to use is the URL library request module. This is another Python module. We are going to use the URL that is HTTPS. Like, we're just going to use this really. It's just going to check out, we're just going to look at this web page, right? So here, this is the address of this web page, and if we go here on show source, then we see the source code for this page, and we're just going to download it with the Python script and inspect it. So we say the URL is this is our base, and then plus this address. So let me show you this thing. URL. This is just the address that we want to look at and request information from. The request is going to be URL. Sorry, library request dot request, and so you just have to know the syntax here. And they also want some more fake information that I will give them. I tell them I'm not coming from the Python script, but I'm coming from a browser. Then they are more eager to respond. So that's my claim, and the page that I just showed you the code of, we acquire also with some functions here, .url open, and then we take the request that we just got, and then we're going to read it, and I will also convert this to a string so we can inspect it easier. And so I can also show you this. I will print this here. I read what? Read. Okay, so this is the source code from the page, the HTML page, and what I'm interested in. So here is my hack that I came up with. If this is some random, if I change this a little bit, C3A, then come to some Ethereum address, which is just another random address, and this has not been used. On the other hand, if it has been used, then information shows up here. So for example, it says something happened 400 days ago, right? And for that reason, what I can do is I can look at the page, and I can figure out if that has been used in the following way. I can say is used, so this is my boolean, should just be is the word days actually in the page, because if I convert it to a string and then check is the word days in the page, then it means on this web page it says some days ago something happened. And this way I can query if there's a balance without actually using an API to a node or actually downloading the blockchain myself, just abusing the Etherscan thing. But this is a super inefficient, of course, but it's just a nice hack around, I think. Okay, and so we are going to print this, whether if it's used or not. And indeed, it has been used, right? The 77th address has been used. On the other hand, if I like, change this to some other private key, like the one starting with AA and then a bunch of zeros and then 4D, this is just another private key, and I run this again, then it would surprise me if that has been used and it sees, hey, this has this private key corresponds to a public key and to an address where nothing ever happened. Okay, so I stayed under an hour. I guess that's okay for the content we covered. I hope that thing shines some light on how all these things play together, and you have a better understanding of private keys now. I never know what my target audience really should be. But nevertheless, thanks for watching. Subscribe and see you next time.